Everything's on, right? All right, physics. This is Physics 1C, the second hour for March 16th is today. And what we're going to be doing now is we're going to start putting capacitors into circuits, but we're going to kind of put them in combinations. So combinations of capacitors is what we're talking about now. This is the primary type of thing that you're going to be doing on your homework. So we're going to be combining capacitors in connections that we're going to call series and parallel. So we're going to start off with, I guess series is probably the easiest to start off with. I don't know. I think parallel is actually probably easier. Now let's do series. I think it makes more sense. Okay. All right, what do I mean by series? By series, I mean you connect capacitors in a line. And what that's going to look like is something like this. So I'm just going to start, instead of drawing plates, I'm just going to start using circuit symbols that you're going to see show up in your homework and stuff like that. So we take a capacitor right here. That's our capacitor, just these two bars right here. I'm going to say this capacitor has a capacitance that we're going to call C1. We'll give it a value later on. And we're going to connect it in series to a second capacitor that's going to be right here that we'll call C2. I think I'm going to write the letters down here and then move this one. Nope, that didn't work. Move this one down here. So these two capacitors, they're connected in series. That just means they're connected in a line like that. And then we're going to connect them up to a battery. Now the symbol we're going to use for batteries in this class actually looks a lot like the symbol for capacitors. So I'll try to make sure that it's clear. It's going to be one long line that's going to represent the positive side of the battery, and then a very short line that's going to represent the negative side of the battery. So this is our battery. And the battery is going to have a potential difference that we're going to call delta V. And because it's connected up like this, there's going to be positive charges that show up on this plate right here. There's going to be negative charges that show up on this plate over here because they're connected to the negative side of our battery down here. I'm just going to draw over here that this symbol is a battery. It could also be a voltage source. It could be a DC voltage source, but we'll just say it's battery. And then this symbol is capacitor. We'll have little symbols like these for all the things we learn about in this class. My hand is really cramping up today. Okay, so that's our setup. And I've only drawn the charges on one plate because I want to talk about how the charges are going to get to the other plates. So the left side of the capacitor on the left plate, is directly connected to the battery. So hopefully it seems reasonable that this capacitor plate should become positively charged. The negative charged right plate of the right capacitor is coming from the fact that it's connected to the negative piece of the battery over here, right? So what's going to happen in between? Well, because I have a positively charged plate right here, that technically sets up an electric field. That electric field is going to have the effect of drawing negative charges, right, along this wire in this direction. Does that make sense? You got positive charges here. It's going to pull negative charges to it. And it will do so until an equilibrium is reached. Until there's enough negative charge over here that we have the same amount of positive charge on this side as we have negative charge on this side over here. Likewise, whatever charge we have on the right-hand side over here is going to be the same negative charge. And because these negative charges came from this left plate of C2, this one will end up being positively charged. And then the flow of the charges will stop. And the system will be in equilibrium with, I didn't draw them in here, positive charges and negative charges, positive, negative, like this on our plates. Okay, does that make sense? Hey, I just noticed was it like that before? The chat is getting cut off for some reason. I don't know why. Fix this real quick. I'll make this like 650. That looks better. And then it's like it got moved a little bit too. I wonder why that happened. I'm having a lot of issues with this, with how I'm doing this Discord chat thing and how it's showing up on the screen. So apologize for playing with that, but it seems like every other day when I come in here, it resets the settings. I don't really know why. Okay, regardless. We're back and set up. Okay, anyone have any questions? Yeah, I actually set it up before class too, so something happened. Yeah, I don't know. Who knows? Doesn't really matter. It doesn't take that long to fix it. Okay, anyone have any questions about this setup? The charges on both plates end up being exactly the same in this case, even though they have different values for the capacitance. So this could have a huge capacitance, and this could have a small capacitance, but you're going to get the same charge on all the plates. So that's going to be one of the things that we know about a series combination of capacitors, which is when the capacitors are in series, the charge on each plate is going to be the same. Okay. So given that setup right there, what we'd like to do is we'd like to know if we can take these two capacitors, C1 and C2, and kind of squish them down into one capacitor. So we'd like to find what we want to call the equivalent capacitance. And that would be if we were to take this circuit and imagine that we could reduce it down to a simpler circuit containing only one capacitor. And then we'll say that that capacitor will have a new capacitance that we're going to call C, and then we'll put a little subscript down here, EQ. And that's what we want to figure out. What is CEQ equal to? All right. So in order to do that, let's talk about the voltages on these plates. Now, if they both carry the same charge, what do you think is going to happen with the voltage on these plates? And I want you to remember that everything that we're doing today is always going to come back to this equation right here. So if the charges are the same, but the capacitances are different, what's going to happen to the voltage on each plate? Will the voltage on each plate be the same, or will they be different? Are they going to be the same, or are they going to be different? Are they equal to each other?
I think they would have to be different.
Okay, why would they be different?
The charge on each is the same, but their capacitance is different. So therefore, for the charges to be equal, their voltages need to be also different.
That's right. That's right. And you can see it if you just rearrange this equation a little bit here. Delta V, for example, for the first one, would be equal to Q divided by C1. That would be delta V1. And delta V for the second one would be equal to Q divided by C2. So the only way these would be the same, there's only one time that they're going to be the same. And when would that be? What would have to be true about our setup here in order for these two to be equal to each other? In general, they won't be equal.
Capacitance must be the same.
Yeah. If these were equal, if these were the same capacity, if this was 10 microfarad and 10 microfarad, then the voltage would be the same. And let's see if you can figure out what it would be. Suppose that I chose this to be equal to something like 9 volts, let's say. And I tell you that these have the same capacitance. What do you think the voltage on the first one would be? And what do you think the voltage on the second one would be? If they were equal to each other. Would they both be 9 volts? Would they be something else? Did that question make sense? Suppose I make this battery 9 volts, and I tell you that these have the same capacitance. Maybe we pick a number to make it easy, because I know you'll be, if I give you a number, you'll definitely be able to figure it out. So let's just pick a number. Suppose that they're both equal to 1 microfarad, okay? Suppose they're both equal to 1 microfarad, and I say that this is 9 volts. what's the voltage on this one going to be, and what's the voltage on this one going to be? Oh, wait, that's actually not going to help you. You need to know the charge. Yeah, I think this is a little too early to be asking this question. We'll come back and we'll ask that question in a second. So let's just go with this. We start off with, on the left-hand side, we have delta V1 is the voltage across the first set of plates. Delta V2 is the voltage across the second set of plates. And what I'm going to say is that if you were to measure the voltage across both of the plates, across both of the capacitors, you would get 9 volts. But if you measure the voltage across just one of them, you get something smaller. So in general, what's going to happen is that the connection between the voltage 1 and voltage 2 is that the total delta V of the battery is going to be equal to the sum of delta V1 plus delta V2. That's what's going to happen. Okay? And as a result of that, so basically the voltage drop across this one plus the voltage drop across this one is going to be equal to the voltage here. All right? So delta V1 plus delta V2 is equal to delta V. We could replace delta V1, here let's go downwards, with this equation right here, Q over C1. For this one, we can replace delta V2 with Q over C2. And now I want to look at this picture here. Our goal is to find equivalent capacitance. Okay? That's the goal, is to find equivalent capacitance. And for the equivalent capacitor right here, it's going to carry the same charge Q, and the relationship between delta V, CEQ, and Q is going to be this. Delta V should be equal to Q divided by CEQ, the equivalent capacitance. Same kind of definition we're using over here. If we plug that into the left-hand side of this equation, we'll get Q over CEQ is equal to, we can factor a Q out of these terms here, so Q times 1 over C1 plus 1 over C2. The Q's cancel from both sides, so we end up getting this relationship. We get that 1 over CEQ is equal to 1 over C1 plus 1 over C2. Or we can write it as this equivalent capacitance of our combination, which is to say, I could take these two capacitors and I could replace them with just one capacitor and it would do exactly the same thing, would be equal to 1 over C1 plus 1 over C2, and you have to take that whole thing to the negative 1 power. And in general, if you have more than 2, the equivalent capacitance is going to be 1 over C1 plus 1 over C2 plus 1 over C3 plus ... all to the negative 1 power. That is our equivalent capacitance. So for example, in this problem, if we had taken, for example, C1 to be equal to, let's say, 3 microfarads, and we took C2 to be equal to 6 microfarads, right? Then we could find the equivalent capacitance down here by taking 1 over 3 plus 1 over 6, raising that to the negative 1 power. And for our particular choice here of 3 and 6, we would get equivalent capacitance would be, let's see, a third plus a sixth is like, I think you're going to get 2. Is that right?
Right.
Notice that CEQ is less than C1 and it's less than C2. In general, CEQ is always going to be less than C1. It'll be less than C2. It'll be less than any of the individual capacitors. No matter how many things that you combine together, the equivalent capacitance will always be smaller. It will always be smaller than the smallest capacitor, basically. See here, our smallest capacitor was 3, and the equivalent capacitance was 2. You can pick any numbers you want here. It doesn't matter what you pick, but the equivalent capacitance will always be smaller than the smallest capacitor. So by combining capacitors in series, the effective capacitance, the total capacitance, the equivalent capacitance whatever you want to call it, is always going to be smaller than the smallest capacitor. Something you can use to kind of check your answers as you're doing these things. Okay. Does anyone have any questions? So let me ask my question again that I was trying to ask earlier. Let's change these values. So suppose that I tell you that capacitor 1 has a capacitance of, let's just make them both 3. Let's say that I make this 3 microfarads, and I make this 3 microfarads. All right. What does the voltage delta V1 and delta V2, how are they going to be related to each other? What do you think?
Would it be like 4.5?
Yeah, it'd be 4.5 volts, right? So if the capacitors are equal to each other, you're going to get equal voltages. Does that make sense? You're going to get equal voltages. And I don't know which one of these equations you'd want to use to prove that, but you could really use any of these. Like this one, for example. If C1 and C2 are the same, this would be like Q over C plus Q over C. So it'd be 2Q over C, which means Q over C would be equal to delta V over 2, right? Let me work that out in case that wasn't clear. So if I let C1 equal to C2, right? Since Q is already equal, then what we end up getting is that delta V ends up being equal to Q divided by 2C. I left out the V for some reason. Right? No, that's not how that works at all. Sorry. We're just not going to skip any steps. This would be Q over C plus Q over C, which should be equal to 2Q over C, not Q over 2C. And then that means that Q over C should be equal to delta V over 2, right? But Q over C is the same thing as delta V1 is the same thing as delta V2. There we go. Which is equal then to delta V over 2, which in our case would be 4.5 volts. So no matter what the value of the capacitance is, it doesn't matter as long as they're equal to each other, right? As long as they're equal to each other, then that means that you're going to get 4.5 volts on one and 4.5 volts on the other one. Does that make more sense? If they're equal to each other.
Mm.
Now, if they're not equal to each other, then you're going to get the voltages are going to split up according to the size of the capacitance, right? So, for example, what if we let one of them be twice as big, okay? So let's let C1 be equal to 2 times C2. And I would like for you all to make a prediction as to what this is what's gonna happen here. If I make C1 be equal to twice as much as C2, okay? So that would mean that I make, just to use numbers here again, let's say that I make C1 equal to 6 and I make C2 equal to 3. Which one do you think is going to have the larger voltage? C1 or C2?
C1.
You can look at this
C1.
equation if you want. You guys think C1? Okay, let's work it out and let's see what happens. So if we let C1 equal
Oh wait,
to...
no. C2.
You immediately...
C2, yeah.
You immediately figured it out. It's inversely proportional, right? Inversely proportional. So your argument then would be that C2 would have the larger voltage. Now, how much more? It has to be proportional to these things, right? So if this is double this, wouldn't it make sense that this would have half as much? Or sorry, this would have twice as much, right? So how are they going to distribute? What's delta V1 going to be and what's delta V2 going to be? What's your prediction? You're saying this one's bigger, right? Because the capacitance is smaller.
One's going to be 6 volts, the other one's going to be 3.
Okay, so here's your prediction that this one would be 6 then, and this would be 3?
Yeah.
Okay, let's see if that happens. So if we let C1 equal to C2, and we go through this equation again, I'll go through all the steps. Delta V1 delta V total is equal to the sum of delta V1 plus delta V2. we replace delta V1 with Q over C1. We replace delta V2 with Q over C2. That's our delta V. But now we've said to let C1 be equal to double C2. So this means this is equal to Q over 2 C2 plus Q over C2. That's delta V. But then we can, how do we add these? This is going to be a half plus 1, so it's 3 halves, right? And that's equal to delta V. So that means that Q over C2, which also happens to be equal to, so let's take steps here. Q over C2 would be equal to 2/3 of the voltage, and Q over C2 is also equal to delta V2. So if our voltage is 9, it's 2/3 of 9 volts, which would mean that delta V2 would be 6, right? And I think that's what you guys said. You all said it. Yeah, 6 and 3. So basically the way that the voltages are going to split is going to be dependent upon the size of these, and it's going to be inversely proportional to the C2, right? Okay, so try to remember that, because I'm going to quiz you on that here in a little bit. We'll use FET, the simulations, to kind of to revisit this idea, and we'll see if you can make predictions properly with those. Okay? All right, so anyone have any questions about these series combinations of capacitors? The biggest thing to take away from this, there's two things, I guess. There's two really important things. I will kind of box them up. There's this one. Remember this. When you have a series combination of capacitors, the charge on each plate is equal. And this one. That the equivalent combinations, the equivalent capacitance is going to be, you add up the inverses and then take this to the -1 power. Okay? All right. So we're going to talk about parallel combinations. Then we'll play around with FET a little bit, and then we'll do some problems. This one might be a little easier. I don't know. We'll see. So parallel combination is going to look like this. We'll have one capacitor here that I'll call C1. I'll have another capacitor here that I'll call C2. And then down here we'll have our battery. We'll say as a potential difference, delta V. We'll connect them up in parallel. So a parallel connection looks like this. A parallel connection is made such that each of our capacitors gets its own direct connection to the battery. This is how your home is wired. So that when you plug something in the wall, you're connecting it in parallel with the rest of the circuit of your house, the rest of the network of your house. And that's why there's 2 holes instead of just, well, I don't know if that explains it, but either way. Point is that the devices in your house are designed so that when you connect them to the wall socket, they all get their own access to the potential difference of the wall socket, which is like 110 volts, right? Every device gets 110 volts. That's to compare it to what we just did a second ago. Notice that when we split up, when we made these different from each other, right, that each of these objects got a different amount of voltage, right? When you plug your laptop or your toaster or your microwave into the wall socket in your house, you don't get different amounts of voltage from the wall socket, right? You always get the same amount. In fact, notice also that when you connect things in series, it reduces the voltage that you get for each piece, right? Like this was 9 volts, but this only had 3 volts on it, right? It's almost like it's not getting as much energy as it possibly could. When you connect things in parallel, what happens is that they both end up with exactly the same potential difference. So delta V on this one is going to be delta V, and delta V on this one's going to be delta V. They'll be the same. So this is one of the pieces about parallel combinations that's important. This is important not just for capacitors. It's also going to be important for resistors and other things that we do later in the class. So when connected in parallel, the voltage across each element is the same. So, okay, does that make sense? One thing I'll point out about this is that if you took a voltmeter, so usually we use the symbol for a voltmeter, and to use a voltmeter you need to have a connection to your wires. You have to have like maybe one connection here, and maybe one connection like over here, for example. And then it reads out on the voltmeter how much the voltage difference is. If I was to connect a voltmeter between these 2 points, it's going to give me the voltage of the battery. So if this was, for example, a 9-volt battery, my voltmeter would read 9 volts. Okay. However, if I were to take my voltmeter and I were connected between here and here, and if I told you that this wire right here is a conductor, okay, and that the system is in equilibrium, I left off something here. We need to put some charges on these, don't we? We need to have some charges on here.
Would it be 0?
Yeah, the potential difference between these 2 points, if the system is in equilibrium, is going to be 0. And part of the reason why is because it's a conductor. These lines represent wires. Maybe I didn't make that clear enough, but these lines represent wires. And this would read out 0 if I connected between these 2 points right here. Because one of the things we learned about conductors is that when they're in equilibrium, and such systems with capacitors are systems in which the conductors are going to be in equilibrium, that the potential difference between 2 points in a conductor has to be 0 so that the electric field inside of here can be 0, right? The electric field inside the conductor has to be 0, so the potential difference between the 2 points has to be 0. If you don't remember that, that was the idea that if I take a conductor and I tell you that it has charges on it, we know that the electric field inside is 0, and we also know that inside the potential is a constant. So if it's constant, then delta V between these 2 points is 0, right? All right, so given that that's the case, one thing we can take away from this is that if I were to take my wires that I drew here for my voltmeter, and I were to connect those wires like up to here, and then up to here, they would also have to read out 9 volts, okay? And part of the reason why is because the potential difference, for example, between this point and this point is 0. And the potential difference between this point and this point is 0. So putting my voltmeter here is no different than putting my voltmeter here and here, right around the battery, where it would measure 9 volts, basically. Okay? Because the potential difference is 0 between these 2 points and 0 between these 2 points because of the conditions for conductors in electrostatic equilibrium. And that's part of why you get the same potential difference between these 2 points and these 2 points right here. Okay? Now, I'm going to erase all these lines that I drew, but that's just my way of kind of describing why it is that you get the same delta V, the same voltage drop across both of these capacitors right here. Okay, so voltage across each is the same when you connect things in parallel. Please try to remember this. It's something that you're going to forget, but just when you see connections like this, just remember that voltage across each element is the same. All right, so the next thing we want to do is to work out what the equivalent capacitance of this would be, okay? So the idea, again, would be that we're going to reduce this whole system down to just one capacitor that will have an equivalent capacitance that we'll call CEQ. It's still going to be connected up to the same battery source, the same voltage source, delta V, like this. And our goal is to calculate what is this equivalent capacitance, all right? Now, in order to do that, we have to know something about the charges on these plates. So I'm going to call the charge on this plate right here to be Q1. And I'm going to call the charge on the plate at the top to be this will be Q1. And the other one will be Q2. My bad. So this is Q1 and this is Q2. Now what we know is there's a connection between these things. Q1 is going to be equal to C1 times delta V. And Q2 is going to be equal to C2 times delta V. I don't know if you all can hear that phone. Come on, let's make it stop. Q1 equal to C1 delta V, Q2 equal to C2 delta V. Like that. And when we combine them together, there's going to be some charge that they get when they combine together here. Now, what I would argue is that if I were to take, for example, a little box, whoops, I don't know how well I can draw this in here. If I was to take a little box and just box in the left-hand side of my capacitor plates right here, and I just look at those right there, the total amount of charge that I would have within a little box would be Q1 plus Q2, right? And I would argue that if we were to smush these two objects down together, such that both of the left plates became one object and both of the right plates became one object, that they would have to be related to this final charge that we get over here. And I would argue that basically this would be the relationship. Q1 plus Q2 should be equal to the total charge that you get over here. Because effectively, when we say equivalent capacitance, this is the language that your book and other books like to use. We really mean the total capacitance, basically. And here we basically mean the total charge that you get when you combine these two, okay? So I would say that Q1 plus Q2 has to then be equal to the total charge here. I left off the subscript. All right, you can call it Q total if you want. I think that's definitely a good thing to do. Now from our equations up above, we know that Q1 is equal to C1 times delta V. We know that Q2 is equal to C2 times delta V. And we know that Q total would be equal to, look over here, the capacitance is CEQ, and the voltage is delta V. You'll notice that delta V shows up in every single term, which means that C1 plus C2 is equal to CEQ. And the general rule is when you have capacitors that are attached in series, if you want to find the equivalent or the total capacitance, you simply sum up the individual capacitances. So if C1 was equal to, let's say, 2 microfarads, and C2 is equal to 4 microfarads, what would CEQ be?
6
Six.
micro.
6 microfarads. You just add them up. Really simple, right? It's really simple. So does anyone have any questions? All right, let's play around with PhET and see if some of these, if we can make some kind of predictions about what the values of things will be. So for this, so you've got, I don't know if I want to use this one or not. I think I instead want to use, I thought that I pulled it up. Where, I think it's this one. I think this is what I want to use. I think I can make this bigger too. Alrighty. Should I build this from scratch so you actually understand what I'm doing? Probably. Yeah, we'll just reset it. So this is another one of the PhET things that we can play with. This one's really nice because it has really almost everything that we need for studying what we're studying in this class. It's got wires, resistors, batteries, light bulbs, switches, AC voltage, inductors, capacitors. Now, all we care about right now are capacitors. Okay, so let's start off with these. So they're represented by parallel plates. We've also got a little voltmeter over here that we could use. And what I'm going to do is I'm going to change the capacitance. It starts off at 0.1. I'm going to make one of these 0.2. Done. And I'll make sure that it shows the capacitance. I'm going to make the other one 0.1. Just leave it as it is. We're going to connect them first up in series here. Of course, it got rid of that, so we'll have to come back and put it back in. So these are connected up in series. They're not charged yet because we need a battery. So we'll drop battery in here. We're also going to use a switch so that we can turn them on and off if we need to. So the switch basically is just a little lever that does this. This doesn't do anything because you need a full, complete circuit to actually get them to do things. All right, let's see if we can do this. Show value, show value, show value. So this is 9 volts. I guess that's fine. I guess that's fine. Okay, we kind of already did this. Let's see if you remember what I said. So I'm going to charge these up. They're going to get charges. It should appear as if there's an equal amount of charge on this plate as there is on this plate, just visually, hopefully. So first of all, we'll test to see if some of the things I told you were true. First of all, let's test to see if so if I connect this red wire right next to this black wire right here, what's the readout on the voltmeter going to be? So I'm going to connect it right here. Should read 0? It does. It reads 0. It's -0, which doesn't really mean anything. We could turn them around and it'll read +0, whatever. What's it going to read if I put the black one here and I put the red one right here next to the battery? What's it going to read?
It should be 9.
Yeah, 9 volts. This thing basically measures the potential difference. It measures the voltage, and the battery has 9 volts, right? All right. So now if I put it around both of these, notice that it's also 9 volts because, again, it doesn't matter where I put this in this circuit. This side is like 0, and this side is like 9, so the difference is always 9. Okay, so what is it going to read? Okay, first of all, which one is going to have the bigger potential difference? Is it going to be the 0.1 farad or the 0.2 farad?
0.1.
Yeah,
Okay.
0.1.
And how much is it going to read? If I put my voltmeter, I'm going to put it right here. What's it going to read? You can try to type in the chat before you guys say anything. Let's give people a chance. So I want you all to type in the chat what you think. If I put this red meter right here, what is the voltmeter going to read when I do that? Go ahead and take a guess what you think it's going to be. If you think it's going to be 9, type 9. If you think it's going to be 4.5, type 4.5. If you think it's going to be 3, type 3. Whatever you think it's going to be. Just type something. Just take a guess. What is this going to read when I put this on here? Only 2 people have guessed. I'm going to wait until like at least 10 people have. Just make a guess. I don't at all care if you're right or wrong. The whole point of this kind of stuff is just to get you to guess. And I want you to guess what you think, not what you just see other people typing. See 4 people. Okay, so let's see what we get. I appreciate all of you guessing. That's good. So let's see what it says. All right, 6 volts. A lot of people said 6, and they were right. If you got it wrong, that is totally okay. So if this one is 6, what does the other one need to be? So we know the total's 9, right? So what are we going to get when we put this one on here? They have to add up, right? So this one has to be 3 then. Now you can think of potential as being, depending on what you read, you're going to see the phrase potential drop sometimes, okay? And that's because electric potential is kind of like a hill in the sense that a hill has drops on it, right? You start at the top of a hill, you go down the hill a little bit, you've changed your elevation, right? So let's just pick some numbers here to help you understand what's going on here. Let's just define the starting point of this battery to have a potential of 9 volts, okay? And let's say that the ending point of this battery has a potential of 0 volts, okay? And again, if you don't understand what voltage means, you can replace those numbers with like elevation. Think of the positive side of the battery as the top of a hill that has a height of 9 meters. And think of the right side of the battery as the bottom of the hill that has a height of 0 meters, okay? And you come to here, and the height is still 9 meters. And then when you get to here, it's saying that there's a change of 3 volts, okay? So if I wanted to assign an absolute value to the voltage at this point, I would say if the point on the left is 9, the point on the right would be 6. Does that make sense? It's like a drop of 3. It's a change of 3. You're going down by 3. And you can see that it's negative, actually, if I did it this way. Might even be a better way to do it, I think. The change is 3. So you start from 9 on the left, and now you're at 6 on the right. Now, if I know that you go from 9 to 6 over here, then I have to go from 6 down to 0 over here, because this is 0 at the end. This point is 0. Okay, so it's literally like a hill. It's little voltage drops. All right. Okay, so let's see if let's try different values to see if we can test to see if you all understand. So essentially, the voltage drop ends up being proportional to the size of these things. The one that's smaller, just remember this: the one that's smaller is always going to have the bigger voltage drop. Okay. All right. So let's change these. Here, let's open this up. And let's reset dynamics, which will get rid of the charges. You could also get rid of charges by just connecting a wire across them, but It's easier said than done. All right, so now what we want to do is let's change the capacitance. Let's do a ratio of like 1 to 4 if we can. So let's make one of them 0.05. One of them will be 0.2. And then in order to get some nice round numbers, let's change this to 10. We could do 40. 40 would probably be a good number. Let's do 40. Okay, now let's show all of our values. Okay. This is what we want to do. Is 4 to 1 what we want to do? Or do we want to do 3 to 1? We want to do 3 to 1, actually. Let's do 3 to 1. Okay. Let's see if we can figure this out. Okay, so now we got them connected up. Let's charge them up by throwing the switch. Boom. You get some fire because there's no internal resistance in these things, so the charges move really fast, and it indicates that with fire. Okay, bigger voltage by a factor of about 10 or 4. So there's more charges on here now, right? So let me just ask, which one is going to have a larger voltage drop? Is it going to be the 0.05 or the 0.15? Which one, when I go here to measure these, which one is going to have the bigger voltage drop?
0.05.
0.05. Okay. So let's use that larger one and tell me. Now remember, the 40 volts gets split up proportionally between these two, right? It gets split up proportionally between these two, right? So just again, don't say anything out loud, but just try to think for a second and type in chat, what do you think the value of the voltage on the 0.05 is going to be? And what do you think the value of the 0.15 is going to be? You can answer whichever one you want to answer. How is that popping up if I closed that program? That's so weird. Okay, which one's going to be 30? You all saying the 0.05 will be 30? And then what's the 0.15 going to be? 10. 30 and 10. Okay. 30 and 10 are good choices because they add up to 40, first of all, so that's good. And since the ratio is 3 to 1, we would think that the ratio of the voltages should also be 3 to 1, right? But the 3 is going to be this one, and the 1's going to be this one. All right, let's check. 30 volts on the 0.05. You all right about that? And 10 volts on the 0.15. So good job. Does that make sense? How it's basically splitting up the voltages? It seems like people are getting it now after seeing the second one. Okay, so we could continue and we could try more. You know, I can make a ratio of 4 to 1. I can make this 50. We can do that real fast. I'm not going to... If we go to 50 here, done. We need to reset dynamic. Oh, let's see. Now we want to make a ratio of 4 to 1. So this one would be 20. Which is the maximum we can get. Show value again. Okay, so and then we show value for this one. Okay, 50 volts, ratio of 4 to 1. So what does this one need to be on the right? 40 volts, yeah. So this should be 40. And it's not... wait. Hold up. I forgot to do something. There we go. 40 volts and 10 volts. So there we go. All right, so let's see what we can do with parallel. Do we want to do parallel too? Parallel is not as interesting because the voltages are the same. It's going to be the charges that are different. And I don't think you can show the charge on this, so we're not going to be able to get as much. So maybe we'll just stop with that, and then when we come back, we'll do problems. So I'm going to throw on the board the problem that we're going to do, and we'll take a break. Where is it? Oh, yeah, I put it way down there. That's right. It's down here. Right there. So this is the kind of problem you're going to see show up over and over and over again in your homework. And we'll talk about how to solve it. And let's shift the solution off to the side. Oh, but you gotta be able to see this part. There we go. All right, taking a break until 4:10. No, we'll do 4:07. We'll do 4:08 because by the time I actually start the break, then